all across quantum communication that way. Clients who are actually interested and curious about what they can do with it. So hopefully I will try to tell what we learned working with them today. Maybe Marc,
introduce myself? Yeah. Thank you, Jean-Francois. I'm Marc Kaplan. I'm the CEO and founder of VeriQloud. We are a startup based in Paris. We develop solutions, both hardware and software, but let's say the most innovative part is the software. For quantum communication, ranging from QKD all the way to quantum internet, connecting quantum computers over quantum networks.
Hi, my name is Erven. I'm the CEO and one of 4 co-founders of KETS Quantum Security. We're based in Bristol, UK, and we're the leaders in chip-based quantum safe solutions.
Denis, CTO and co-founder of Qrypt. I'm a physicist by background, spent 20 years in the intelligence community. We build quantum secure and quantum safe encryption systems, modernizing encryption infrastructure that you see out there in the world today.
Okay, so maybe we can get started the discussion, and I would like to start with, let's say, some commercial updates. We talk a lot more about, I mean, there are different days, Y2Q, Q-Day, some people come with new names all the time, but I think we see that the threat of, quantum computing is becoming more real. We saw the executive order in the United States, so all the US government has to transition to PQC for the moment by 2035, which is a massive undertaking. And I can see from my side, from my clients, they are asking questions about should we also consider quantum communication as part of our toolkit in that regard. And I would like to know if you see some additional or some increased commercial traction based on those developments compared to last year, for example. What do you feel? I mean, anyone can start on this one, but
I just want to say something about Y2Q and Q-Day. Just because Harvest Now and Decrypt Later makes all the news today, and it's really not just quantum computing that's the threat. It's all the corrupted infrastructure. It's the libraries, it's software that we use. And that's been going on for more than 50 years. It's just that quantum computers bring a brute force mechanism where you absolutely know that you can break the system. But Q-Day is really about the day when all that encrypted traffic that's been stored on Chinese servers gets decrypted and operationalized and monetized. That's a date in the past. Your data is gone. You can't re-encrypt it once it's been taken. So just setting the stage for what that really means going forward, we need to transition past this older architecture and infrastructure that we use and start using some of these tools like QKD, which unfortunately, as you know, in the US, despite the executive orders, NSA has an objection to deploying QKD on federal government systems, even though it's funded in huge national labs and test deployments. So we really need to overcome that. It really needs to be something that we incorporate in the future of our networks, not just PQC. There has to be a place for QKD. It has very different security assumptions, much better and stronger, permanent, everlasting security that we need for the future. We can't just rely on another single point of failure like this next algorithm that we're transitioning to. That's my soapbox version of Harvest Now, Decrypt Later, and Q-Day.
And in terms of the traction, absolutely, like the last 12 months has been night and day in terms of the inbounds, and some of them are from the natural places you'd expect, sort of the QCIs of the world, the national sort of quantum networks that are being set up, but also other places that you might not expect, lots of banks and financial institutions, telecoms, data centers. I mean, it's been a huge, huge increase the last 12 months, which is great to see.
Yeah, what I can add on that is that indeed there is a, I mean, in the EU you have this strong push from the European Union to build national infrastructures with various involvement from the states themselves, ranging from no involvement in France, for example, to 100% involvement in Germany. But what we see also like more and more interest after doing these first demonstrations and showing how these connections can be done in practice. We see more interest also from large institutions, in particular banks, that are asking. how should I do? What are the first steps that I need to perform to get connected?
And actually, another key thing you sort of mentioned, Germany there, that's happened recently is this common common criteria protection profile. It's been developed by ETSI. BSI's had a huge hand in it, and this is really a key sort of chicken and egg where people want third-party security of our systems, and you need a profile to sort of protect to test them against. So these third-party assurance providers can test against a common thing. We haven't had that, and partly it's been sort of until you have the volumes, you can't get this. So we've finally broken out of this chicken and the egg where we now have something to test against. It'll help increase the volumes, and it'll help get a better protection profile. So we're finally in a good part of the feedback loop now that we've finally sort of broken this cycle and have something to test against the world over too, because you don't want a different test in Germany than the UK than in the US. It's a common thing that we can use now.
So if we look at the stack of quantum communication and networking, it goes really like very large scale, like QRNG, but you can use actually also for the PQC solutions, right? So it's an opportunity from that standpoint, right? To down to let's say the very the QKD nodes and channels. Where do you see traction and opportunities for you? Do you see, across the stack, where are the use cases and the most where you have most traction?
Well, I'll say from what we do, we don't build QKD systems. We virtualized it and inverted the model where we put those QRNGs in the cloud and made them available through existing network infrastructure to assemble keys effectively at any endpoint instead of using key distribution the way PQC works. So it's a little bit different, but it would incorporate every aspect of QKD. And the customers that we have now are all big, high-value data industries. It's healthcare, it's banking, it's telecom, and it's government. That's really it. They have the money and the resources to secure their infrastructure at almost any cost. It's more important to them to keep that data safe for decades, not just the next news cycle, which could be a text message being exposed or an email chain. But I know it's very different for QKD, and we love seeing what's happening in Europe that's actually getting built and deployed there, competing with what they've built in China. We really need something like that in the US, and we need the government behind it to really push it, even if it's only for the financial industry or government, let's say, and then have a standard behind it. If we don't have that, it's going to have a lot of trouble getting more than niche traction in the US, despite the government funding it. So.
Certainly, telecoms is an area that you'll find use cases, adding sort of value-added quantum-safe services. It was just a couple weeks ago that in South Korea this launched with SK Telecom offering a subscription-based service, and I guess we're expecting this to see it in Europe as they build their Euro QCI and things like that. Data centers is another huge sort of almost Pandora's box. So you've got co-location services where they really want to keep their different clients segregated and secure, so that's one particular sort of aspect. Or if you look at the hyperscalers, then they're really trying to protect key sort of high-performance compute. You sort of design your jet engine in the cloud and then want to come back out of the cloud and produce it. And this is the type of IP you want to keep secure for 50 years. So certainly that's two markets we see, telecoms and data centers, as being huge, huge players in sort of quantum-safe services.
Yeah, and if I can add to that, I mean, most of it has been said already, but what I want to add to that is that, on the other hand, quantum communication and QKD in particular is so disruptive that it's very hard for people to realize that they need that in the first place. And I think that actually the effort that KETS is doing to make QKD more accessible to end users, it's a heroic effort. It looks like this to me, because this is what you need to convince people they need it, to show them that it's accessible and that they can use it and integrate it in their, without changing the whole process in the first place.
When I talk to my customer, most of the time they don't want to implement those networks. They feel it's too complicated for them. But they are willing to buy from typically service providers. So typically the two providers that they have in mind are telcos. And maybe we could talk more. But for example, there are a few commercial offerings out there, like in the UK, BT has a commercial service. So that would help, I think. I don't know if we can talk a little bit more about that. And there's another aspect is that a lot of our clients use hyperscalers, and they start to say that they will secure the communication from you don't have to know how it's done, but they will secure because as you know they have also networks of data centers, so they also have to secure the communication between the different and they have like dozens and dozens and dozens of them. And so we know for a fact that they're gonna say they secure that. How do you see that as opportunities too? Are you able to play in that part of the value chain?
I mean, securing huge links, data center to data center, we've shown that we can do that. We did a demonstration between Washington, D.C. and a site in Sydney, Australia,
Wow.
Without any dedicated infrastructure. As we have huge amounts of QRNGs in the cloud, and we generate huge amounts of key material at the endpoint. We apply cryptographic extractors, and that is a digital way to achieve the same exact thing that you would get from QKD. Different security assumptions, different model for use, and now you don't care what happens in the middle. Every single piece of fiber, subsea fiber, can go through China, every place else, let them harvest it. The key material was never exchanged across that same channel. So decoupling the key material, which is what QKD does, from the data channel and the data and software that's encrypting it, that's kind of critical to the architecture going forward. So if we can do that, and we heard a great briefing from Marc this morning about how they did that in Berlin, do that, and we've solved half the problem of harvest now and decrypt later. If you have connectivity on one of those nodes from the hackers or nation states, the use of that just goes away. So we're not worried about Eve so much being on that fiber optic channel in the middle and doing that kind of harvesting, especially on the QKD network. That's unlikely. They're going to go after the endpoints, the weak points, and that's really where these technologies can shine in the future.
I think there's also a misconception sometimes where enterprises don't think that they're going to have a device in their own premise. They'll just sort of connect in, I don't know what that last mile is, maybe they have in mind PQC. And that can be one way. I think something that we try and push hard is that with a chip-based approach, it's actually pretty simple on our roadmap to think about shrinking the size of sort of the transmitter QKD device and drastically bringing down the cost. So when you think about a dense metro network, you could give a British telecom or UK, so I'll use a UK example. They have the expensive sort of receivers, a couple of them to get into their backbone network. But then we can have lots of major enterprises sort of buying 1,000 QKD devices to connect up workstations or some of their critical employees and stuff. But I think there's a misconception that it's uniformly expensive and stuff, and it's not the case. I think we'll see end users have the technology to go end to end. And there's already sort of telecoms providers with really good blueprints that do a backbone for themselves, but also let end users connect in. So now DT's got a DemoQuant project in Germany, and their architecture specifically allows not just their own backbone, but also for end users and customers to connect into it with quantum devices on their premise.
We also have, I mean, we have a different approach here to this problem. What we're trying to, I mean, the way we're trying to attract new end users to using quantum communication is also based on a solution that I briefly presented this morning, where I showed how you can combine classical communication, classical quantum communication and classical cryptography to build like quantum enhanced data centers. And what we particularly like about this solution is that it provides you a sort of quantum cybersecurity as a service. And I guess this is very important to, so of course, I mean, it secures the system itself, not the connection with the system, but you can offer some security guarantees using quantum key distribution in a completely virtualized way. And for the end user, in principle, it doesn't have to be more complicated than just pressing a button and say, I want quantum cybersecurity. This is the way to go.
That's great, because user adoption is a key topic, obviously. I wanted to touch also about what are the technological innovations that you are developing, We know that it's still a nascent field, and we have a few limitations. So, for example, distance is one of them. There are some things we need, like repeaters, that hopefully we'll get soon. Can you elaborate on the innovation that you see coming that could unlock more adoption? And you mentioned miniaturization, which is one of them also, to help clients adopt at their endpoints.
Yeah, because I mean, you've got, for instance, like the NCSE white paper back in 2016 succinctly summarized a bunch of stuff to work on, and we sort of took it as our mission to sort of tick off, bring the cost down, bring more easily integrated, make it smaller, that kind of stuff. So all of that is drastically helping the user adoption. And actually, like an overarching point, I think all of us were making when we were chatting earlier, is this is the chance to add something new rather than just sort of do a little bit better algorithm. Yes, it's not to say that post-quantum doesn't have its place and it's an important tool for the toolbox, but you can also enable with these new solutions something that just wasn't possible before, and starts to lay the groundwork for the sort of infamous quantum internet that's going to come.
Yeah, I think we had this discussion earlier in the UK as well. The term quantum internet's a little bit of a misnomer because we won't be encrypting cat videos with qubits anytime soon. And the other issue with commercializing, which again, this is the same thing that happened with regular computers, became virtual machines, and VMware made this available to everyone. Amazon did this with the cloud and server technology. Nicira with software-defined networks, that was all virtualized. Same thing will happen with quantum communications and QKD links. We need to do that and get it down to the end user. Most of the traffic on the internet right now is streaming videos, it's downloading Netflix and so on. That's where that quantum key needs to get get huge commercial traction. It can't just remain these physical links that are just between two data centers or intra-data center. That will never rise to the level of 1% of communications traffic. Where you really need to get to enable this next generation of architecture, we need to transition past the 1970s public key infrastructure that we inherited with a slightly better algorithm. There's no proof it's even hard. We don't know when that breaks again. We have now a chance, a very painful upgrade that's coming, to redesign, re-architect it, and make it much stronger. And that has to include quantum technologies like QKD.
Yeah, sorry, again, I want to add to that. Another message that I tried to pass earlier is that so you mentioned quantum repeaters that are probably far from being commercialized, but they would allow end-to-end quantum communication. I don't know if this is what we need for spreading quantum communication to end users, but what I know is that and what we experienced is that the tiniest step after QKD requires huge research effort. So even before quantum repeaters are there, we identified applications that could be run on quantum networks, and one of the applications that we know is possible to run is to do confidential computing. So these are distributed problems where the parties don't reveal their own input to the problem, right? So we know it's possible to do it with QKD devices. You can buy from KETS and implement it, but there has not been any implementation in a research group so far. The solution is known. Well, it's known for a long time. It's correct for just a couple of years. The correct solution just appeared a couple of years ago. But I mean that even at a research level, going toward more applications, which we believe that in turn would lead to more adoption, I mean, we're not there yet. There's a lot of effort to do also in this direction.
So talking about use case, because we are at the quantum computing conference, so I can't help to ask, but when you look at the roadmaps of the different quantum computing hardware makers, I mean, at some point, and for example, if you take IBM, it's written clearly on their roadmap, so it's 2026. They need quantum communication. It's written, right? So they need. So it's more LAN type of approach, but still, I mean, the technologies are what you are developing could be useful, right? Is there, market you're already looking at, opportunities you're looking at with this, this use case? And then, of course, we talked about the quantum internet. Obviously, we won't exchange quantum. I mean, we won't exchange videos because it's classical information. Also, it's high bandwidth. It's not really great for that. But exchanging quantum state between quantum computers could be that could be a use case, right? That we see on the horizon. Just to make the ER link with quantum computing, what do you think about these two opportunities for you, the technology that you are developing?
Maybe I can start. So yeah, the idea of using quantum communication to link QPUs to scale them is, of course, very important today. It's in the air. I think that most of the problems are on the physics side. I mean, it's very difficult to do, and it's very different depending on the technologies that you use. So one of the questions so I'm not a physicist myself, and one of the questions that I don't know about is how people believe that different types of QPUs will be used for different problems, and this is something that I'm willing to understand more. But what I know is that the linking between the scaling effort is very, very different between the systems. And just to end on this remark, what we do, so we also work in this area, but what we do is more, again, adding a layer of security on the computation itself right now. And what we argue is that if you can give a remote client the ability to, let's say, control this link between the QPUs, then you can also run secure delegated computation. So that's all I can say.
Maybe Chris, you have some.
Yeah, I guess for us, I mean, connecting up QPUs, it's sort of on the order of meters. It's a different problem set because they're going to be able to use all sorts of exotic, I don't know, fibers and connections and stuff like that. I think we think more along the lines of sort of once it's kilometers and things like that. So I don't think any immediately sort of connecting up QPUs would be huge on our mind. It's more about sort of once they're in the cloud, and Marc was referring to sort of encrypted quantum computation, blind quantum computation. You've got sort of user sitting at home, wants to run and solve, I don't know, find the next cancer drug in the cloud. And the sort of the quantum data that's going in, the algorithm being run is almost as valuable as the quantum computer running on it. And that's where maybe we can play a role, because really when you get started on sort of encrypted quantum computation, all you need is a qubit preparer as if you're the user in your house, and that's pretty much a sort of a quantum key distribution transmitter. So I think we think more along the sort of the length scales of kilometers and out, though we'll learn a ton of stuff deploying QKD in the field, throwing sort of photons down fibers. There's lots of quantum internet companies out there that are going to solve the quantum internet, and they've never sort of thrown a photon down a fiber to see what it's like. So I think we'll have some valuable insights, but we focus more on sort of kilometers and out, I think.
I think one of our quantum repeater friends is our neighbor in New York City, and we'll hear about them. So I think that problem solved somewhere already. But I think you're right in looking at IBM's patents and what they plan on doing. It is a meter. It's a entirely quantum computer data center that's modular with lots of quantum computers individually and chandeliers connected by these links. And the use case for connecting them over larger distances, repeated or not, is not the same. So I think you're right on the money. And I don't think it'll ever be as efficient to connect quantum computers over distances like that and use them for parallel processing as it will be on a single chip or within intra-data center.
But maybe picking up on that, and something else you said sort of sparked it in my head, talking to a government type about sort of their national network that they were planning, and so they talked to the academics. Is there anything to still develop? And the academics saying, no, it's all ready to go. And they're asking me, is it ready to go? I was like, no, there's a ton of stuff. Like they might have built a four-node network in a university setting. That's completely different from putting a metro network out there. And then another key piece I think you're seeing recently is it's not just a QKD network. You're adding a software stack that can bring PQC algorithms in. And you have this layered approach and all these tools, and that's a completely different proposition for some of these networks that are now popping up, where you have all of the quantum safe tools at your disposal. It's a rich playing field, and I think it's a relatively new one. Something you were saying sort of sparked that in my head.
Yeah, I think it'll get built. It's just it won't be used for cybersecurity. It'll be used for these other applications that we probably haven't even thought of. I mean, there's a lot of amazing sensing technologies that could come out of something like that. You know, huge networks with single photons traveling down them, probably sense gravitational waves. I have no idea. There'll be somebody really smart will find a way to use that might not just be the things we're talking about here today.
So maybe we could, the last topic I would like to discuss is government support. They play an important role. We know that in Europe there are European programs that are pushing quantum communication. There are also at the country level there are different policies. So I know Germany is very in favor of quantum communication. France is less, and it's still within EU. Not talking about the UK and US, obviously. Then, of course, we have the US. We know that I think $500 million in the CHIPS Act are somehow meant for quantum communication. But then at the same time, NSA is not in favor. So how can we navigate that a little bit better? What is the situation? What do you think? I mean, some things are positive.
I talked to the government a lot, and I just got back from a big DoD event on this cryptographic modernization. And it's really an education process. This is a huge issue for them. They've never done anything like this before. Remember, the internet, their own intranet was minuscule last time a cryptographic transition happened. This is a much bigger problem. And so their high-value target, their high-value data is something that we can't do with QKD, right? A drone platform will never be an endpoint for QKD. Like, I mean, maybe there could be, it could happen, but that's not
hardware.
In 20 years.
Yeah, and then over the horizon, and one of the nodes is for the downlink is a satellite. So these things are intractable problems right now. There are other faster, easier solutions for it, but the transition period, they want to do things. They just don't have, a bunch of quantum physicists, crypto mathematicians sitting around waiting to be like, oh, you have the perfect solution. Let's go do this today. It's not like that. It's a back and forth. It's educating them. It's getting close to that customer and figure out what's a realistic use case. It's not the things they think it is.
And I mean, we deal with the NCSC in the UK, and I try and remember. I mean, there's people behind these organizations, and most of them are mathematicians. So of course they're better suited to vetting some algorithms and don't want to stray outside the bounds and vetting completely new hardware. But on the one hand, they say more has to go into vetting hardware like QKD so that we can stamp an assurance sticker on it. But they it would be a welcome change to tweak ever so slightly the language in some of these things, that you should experiment and start, an enterprise should get involved experimenting now, not in mission critical stuff, with more sort of docile applications so that it can get to the point where it can encrypt mission critical stuff. I mean, this is the NIST process. You'd just like to say the same thing happen for hardware now. So I'd love to develop a roadmap jointly with the likes of the NSA, with the likes of the NCSC about what do we have to hit so that you will trust it with your information and that kind of stuff. I think that'd be a more proactive, productive approach.
So more certification approach that could help enterprise users, because then they would know.
Because this protection profile is huge. I mean, now you've actually got a common standard that any third-party assurance provider can go and we can give a box to, and they will go through and verify whether it does or doesn't meet this common standard. So this is a huge thing that's just come out, and it could have happened 5 or 10 years ago, really, if it hadn't been such a sort of a dampened atmosphere around hardware like this. But I'm glad it's there now, and I hope a lot more sort of jump on that bandwagon and use it.
If there was a standard, it would be huge help, right?
Obviously, I mean, I can't tell.
They're against.
So I don't know if NIST is there, but
well, they're crypto mathematicians. They're not physicists there, so it's a bias.
Oh, you're right. Yeah. Marc, you have some perspective maybe on what is happening in the EU?
About what? About
the different dynamics and
yeah. So as was mentioned, so the EU is operating at 2 different levels. First, I mean, everything that is EU related is very complicated. It's very hard to know what are the driving forces, but you get used to it. So in operational, the plan is to have quantum communication infrastructures operated and interconnected between the 27 member states by 2027. I would say the end of the decade is more realistic, especially it includes satellites.
It's very short term, huh?
It's very short term. Yeah, but the technology is there, right?
Mm-hmm.
The fiber is there mostly, so it's not impossible. At the same time, there are also rather large-scale projects, I would say, considering the next stages, what happens after, when you have repeaters, when you have quantum memories, when you have quantum computers. And this, I mean, the main one is this Quantum Internet Alliance, which is led by the Technical University of Delft, and which develops at the same time the technology like repeaters and end nodes for quantum networks, and trying to identify what are the applications, what will be unlocked at each stage of the quantum network. So it's a rather large organization. I think we are 43 core members, but there is also room for discussion with other companies, including outside the EU. So if you're interested to learn more, contact me, and we can add you to these circles of discussion.
Because the EU is so good at making standards, maybe the standard could come from the EU this time. I mean, the EU is good at that.
Discussing.
Yeah, discussing. I mean, when we look at quantum communication, we can't avoid China because, from what I'm seeing, they are probably one of the biggest actors, but there's not much we know about them. Do you have some insider track of what's going on? I mean, they were the first to launch a satellite that was supposedly QKD secured, right? They have, I think, they claim that they have the largest, network in miles or kilometers, whichever you need to prefer, right? And of course, they know how important security is because they like to hack, the rest of the world. So do you have some information about what's going on and how do we compare to them?
I think last reckon it was what, 2,000 kilometers sort of north to south. I think there was now a 700-kilometer offshoot to the west, and it's an entangled satellite, so they can, again, I think it was 700 kilometers, maybe it was 1,000 kilometers sort of between two ground stations. So, I mean, second to none in the world in terms of their quantum communications network at the moment, certainly.
That was the Messias satellite?
Yeah.
So the issue with that and the 1,000-kilometer record that they broke with their QKD system is that how many keys can you generate in one day? So on a 1,000-kilometer link with attenuation of the single, back of the envelope calculation, they made one AES key every single day. I could have brought you, with the QRNGs that we have available from the cloud, 1 trillion years worth of AES keys on a thumb drive at that same endpoint. So it was a great science experiment to prove that it could be done. But in practice, that QKD endpoint being on a satellite, how much key material can you generate when you could have just deployed it with very different security assumptions with the satellite itself, to the ground station, to the command system for that, where you have a new property. It's unconditional security. You have made 0 assumptions about the channel, about any interference or anything else. So I think it's going to be a long road for what they're doing. I think that trusted node network that they built around China is amazing, but you're physically securing every one of those nodes. That's outside of your firewall, your switches, everything else. That's the endpoint for where the keys are. Now, classically, that key has to get to some place where it's being used for encrypting traffic or files or something, and they can do that. They have the people, and it's working for them. I think it's way more secure than their domestic PQC program, which they've told no one about.
I have no information about China. Nothing I can share here.
Oh, wow.
But no, what I find very interesting is to see, because we're talking about cybersecurity, and of course, what is very important here is how much the user feels that he needs security, and the fact that China leads the way in the whole world sort of radiates around. We see the national programs in Korea. Korea has the second largest quantum network in the world. Singapore, India now has also the plan is to build a connection from from Delhi to the south. So
It's a massive country.
yeah, that's a massive country, right? So it's very interesting to see that maybe it's related. I mean, in cybersecurity, I used to say, I just realized that it's how much relevant it is for QKD recently. That cybersecurity is much more like when you're chased by a polar bear, for example, that wants to eat you. The goal is not to be the fastest, but just to be faster than the other guys that the polar bear could eat.
It's true that that's why I mentioned China, because when you talk about the US, I think the US really pivoted when they realized that China was first in that. So that's where I think the money get dispersed. But then they still are on the old posture where they still prefer crypto.
They call it the Sputnik moment, though.
Yeah.
When they saw the Messiah satellite, that unlocked a lot of money from the NQI and a lot of programs, including some of the QEDC work that we're doing here.
And they do have some networks. I mean, they've got the Chicago Quantum Exchange, where they're, I think it's up to 140 kilometers or something loop. And not to forget, I'm Canadian, so I'll chime in for Canada as well. You've got Sherbrooke's network, connecting up Montreal, Sherbrooke, and
That's right.
Quebec City as well. So there's stuff in North America as well.
Yeah, New York has its.
Yeah, and I think we're going to hear about that. I think the CEO's here somewhere in the crowd. It's hard to see past these lights.
We'll hear about the Canadian network as well later.
It's just not enough. We're certainly behind what China's done, if everything they say is true.
Yeah, but that's the problem. How we can check that? It's another discussion.
They've not published a lot, which is part of the problem. We should be dubious about any company, country, whatever, that does not publish their findings and proofs of what they've done. And we've seen some of that in quantum science just in the last couple of years. People make extraordinary claims without proving it publicly. We should question all of that. If you make claims like that, let's see the evidence of how you actually did it.
Maybe we can open now that we mentioned people in the audience that we can't see. But please ask any questions. We still have a few minutes ahead of us. Anything?
We can't see you.
We can't see you if you raise your hand.
I see two questions here.
Okay, so wherever they are, it's super hard to
It's like looking into the sun.
Yeah, my question is, what are your thoughts on these modern containment-based quantum networks? They do quantum secure communications without the need for trusted relay points. They work with PQC. They can do networking of quantum computers eventually. They'll be able to do distributed quantum sensing connectivity. What are your thoughts on that model, that containment-based model? There's networks out there today, like EPB has got one, Q, which we'll hear about later. There's got one that's containment-based. Thoughts on that?
So the question is, so you can use entanglement to secure communication. It's since Einstein, we know entanglement is a very strange phenomenon that works at huge distances, right? And so the question was, is it a viable path for securing communication? I'm not a physicist, just I know the concepts of entanglement, but that's it. So maybe Chris, you know better than me.
I mean, it's another way of doing QKD. You measure entangled particles. Usually the drawbacks in the field is your rates are going to be a ton lower, and sometimes your distances are lower as well. So, I mean, we do, at least for our first systems, prepare and send, and the security's been shown to be equivalent. And you can do other tricks with optical routing and sort of metro network scale stuff. So it's really a commercial one of what does the customer want in terms of rates and security and stuff like that. But they definitely have their place. And I think this is often the point that maybe the NSA and NCSC forget is we're going to build the quantum internet, whatever that is, and that's going to allow you to establish entanglement on 2 places on the planet. And just by de facto, by definition, you'll be able to do QKD with that resource. So it's coming whether they like it or not. In the short term, though, there's usually some trade-offs with entanglement networks, just purely based on sort of their current technological limitations, which are going to go away.
I mean, I'll just comment that there's a dozen different QKD protocols. I think the one you're talking to is called E92, BB84. There's probably 10 or 12 others I couldn't name. So it's just a matter of choice, like you said, for the customer.
Yeah, apart from QKD, so in this Quantum Internet Alliance, we work a lot on use cases. I would say that for entanglement distribution network, we haven't really identified use cases with a large pool of users. Now there are some niche applications, like for example, if a country was deciding to increase the sensitivity of telescopes using entanglement, which we know we can do, I would find it awesome.